Hey, good to see you again. I'm Mani Khanuja. So last time we filled a GPU up, 16 gigabytes of weights, the rest of the card going to cache, and about 50 conversations riding on it. And now that card is full. The fans are going, the memory is spoken for, and everything about it looks busy. So, are you actually getting the machine you paid for? Because full is one thing and busy is another thing, and neither of them means used. So you can be full and busy and still be getting a small slice of what's printed on that spec sheet. And how would you even know? You'd want a percentage, right? Something that tells you you're getting 60% of this card or 20. And that number does exist, and it's genuinely useful, and it's also the easiest arithmetic in this whole course to get wrong. So why is it so easy to get wrong? Because every percentage has something underneath it. And the whole question is what you divide by. And your server does two completely different jobs. Remember? So it reads your prompt first, and then it writes the answer out one word at a time. So do those two jobs run out of the same thing? They don't. And that's why they need two different percentages. And today is mostly about keeping them apart. And there's one question I want to answer properly before we finish. One H100, that same 8 billion model, one person waiting for their answer, and nobody else on the card. How fast can that answer possibly come out? There's a hard ceiling on it, and nothing you write in your code goes above it. And I'd like you holding that question all the way through. So let's do the reading stage first, because it's the friendlier one. Reading your prompt is compute bound, and we worked that out a couple of episodes back. So the thing you run out of there is math. So how much of your math did you actually use? You take the operations your model really did in a second, and you divide by the operations the chip can do in a second, and that's the whole idea. And it's called model flops utilization, and everybody says MFU. And can you get the top half of that without a profiler? You can. Every token costs you roughly 2 operations for every parameter in your model. And that's the same 2 per weight we counted when we did arithmetic intensity. So 2 times your parameter count times the tokens per second you measured, right? Let's put numbers on it. 8 billion parameters, so 16 billion operations per token. And say you measure 30,000 tokens a second going in, and that's a number off your own dashboard, not one I'm claiming for you. Multiply, and you get 480 trillion operations a second. And what does an H100 do? 989 trillion. So divide, and you're at about 49%. There's a second piece to the top half, and it's the attention math, and it grows with how long your prompts are. It's on screen if you want it, and for ordinary prompts, it's small next to the first piece. Now, why is it called model flops and not just flops? Because there's another version of this that counts every operation the hardware performed, and that one will flatter you. If your server recomputed something to save memory, the hardware count goes up. And did your user get one extra word for it? Not one. So model flops counts only the math your model owes for the tokens you delivered. And the goal of a system is throughput in tokens per second. And nobody's goal is burning hardware flops. So when you write your own number down, write down which of the two you counted, because in 6 months you won't remember. So there are 2 ways that arithmetic goes wrong, and both of them are a number quietly swapped on you. The first one is the number underneath. What's the peak for an H100 in 16-bit? 989 trillion. And you'll see 1979 on that same sheet, and we pulled that one apart last time. The bigger figure assumes structural sparsity. So 2 out of every 4 neighboring weights have to be exactly 0. And has anybody done that to your model? Almost certainly not. So which one goes underneath? The dense one. Put the big one there, and your MFU comes out at half of what it really is. So you'd read 49 as 24, right? And then you'd go and spend a week optimizing a stage that was doing fine all along. The second one is the number on top, and it's sneakier because it flatters you instead of scaring you. When your server runs several requests together, they're almost never the same length, so the short ones get filled out with meaningless tokens to make everything line up. Those fillers are called padding. And does your GPU know their junk? It doesn't, and it goes ahead and computes them for real anyway. So what happens if you count padding in your token rate? A server wasting half its work on filler reports a lovely MFU. It's doing the math, it's just doing it for nobody. So count the tokens you actually handed to a user, and throw away whatever your kernel saw. And if your token rate comes out of the same place your batches are formed, go and check which of the two it's counting, because those can be a long way apart. So that's the reading stage. And now the other one, and this is the number you'll use most days. Writing the answer out is memory bound, and we've said that a few times. So what you run out of there is bytes moved. So is a percentage of your compute any use there? None at all. You want a percentage of your bandwidth. So take the bytes you really moved in a second and divide by the bytes the sheet says that card can move in a second. And that's model bandwidth utilization, MBU. And what do you move to write one single word? We've done both halves already. So it's all of your weights, every one of them, and the whole KV cache for everybody you're serving. Add those, divide by your teapot, your time per output token, and there's your bytes per second. Here's the worked one, and it comes from Databricks. A 7 billion parameter model at 16-bit is 14 gigabytes. Say your teapot is 14 milliseconds. So 14 gigabytes in 14 milliseconds, and that's 1 terabyte a second. And if the card underneath you peaks at 2 terabytes a second, where does that leave you? 50%. And notice what you needed for that, just the size of your weights, and a number your monitoring is already plotting on the wall. No profiler, nothing installed, nothing restarted. So here's the rule, and it's short. Report MFU for reading the prompt, and report MBU for writing the answer. And what if you blend them into one number for a server doing both? Then you've got a number that isn't a percentage of anything in particular. Some teams go as far as running the two stages on separate machines. And this is one of the reasons, and whether that's worth it for you is a module later in this course. One honest thing, and I did go looking for this, there's no published good number for either of these, right? Nobody has a table telling you 50 is healthy and 30 is sick, so don't go chasing somebody's blog post. Measure yours this week, write it down, and watch it. The day it drops 8 points, something in your deployment changed, and catching that is what these two are really for. Let's answer the question I left you with at the top. One H100, the 8 billion model, one person waiting, nobody else on the card. To write one word, your model reads all 16 gigabytes of its weights out of memory. And how fast can that card move them? 3.35 terabytes every second. So divide, and one word takes about 4.8 milliseconds. And that's a bit over 200 tokens a second. And that's your ceiling. Nobody beats it with better code. And it's simply the fastest that answer can physically arrive. And it assumes 100% MBU, which nobody gets. So 60 to 80 is realistic on a good day. And in real life, you'd call it somewhere between 125 and 170. Now put that same model behind different memory, and an A100 gives you about 127 tokens a second. An H100 gives you 209, an H200 gives you 300, and a B200 gives you about 480. So what moved across that row? Not the model and not your code, and I didn't touch the compute either, only the bandwidth. So those two chips with identical compute from last time, here they are again with a tokens per second number on them. And now run the same model in 8-bit instead of 16. Half the bytes, so half the time, so exactly twice the tokens, right? 209 becomes 418 on the very same card. And that 2 times is exact, and it doesn't wait on a clever kernel because the thing you're dividing is a number of bytes and you just halved it. So here's the frame I'd like you to carry out of this one. How much of what's coming in this course is an attack on that one division? Most of it. Serving many people at once spreads a single read of the weights across all of them. And fewer bits per weight shrinks the top of that fraction. And getting more than one word out of a single pass shrinks it another way again. Different techniques, different modules, all pulling on the same number. So, where does that leave you? We started with a card that was full and busy, and now you know that neither of those words means used. And instead of one guess, you've got 2 percentages, and each one belongs to exactly one stage. So what would I do tonight? The bandwidth one, because that's the stage costing you. Take your weights in bytes, add your cache, take the teapot off the dashboard you already have, divide and divide again by the bandwidth on the spec sheet. Write that answer up next to your latency numbers and treat it as your baseline. Your server can hand you the raw counters for both of these too, and those names move around between versions. So we'll do that properly when we get to your metrics. And what does a baseline buy you? Two things, and both of them are conversations. It tells you how much room is genuinely left before you're buying hardware, and when somebody says the server got slower, you can tell them which half of it got slower. And next time we put all of it to work. I'm going to hand you things you'd really see on a bad afternoon, the symptoms rather than the causes, and we'll work backwards from each one to what's actually happening. And you'll be doing the diagnosing. See you next time.